Hello, I want to get some thoughts down on paper about the phenomenon of conjugation, how it is a stabilizing effect, and how we could recognize conjugated systems. And when will we make conjugated systems? When we do an aldol reaction. Conjugated systems, or just plainly conjugation. A molecule has a technically conjugated pi system when you have the alternating pattern of double bonds and single bonds. And so technically, I'm going to call this, what is conjugated? What is in connection with each other? It is the pi electrons. And so really I should be saying conjugated pi system. And this is one possibility. Double bond, single bond, single bond, double bond, etc. So that is the conjugated pi system, meaning that the pi electrons are in the conjugated pi system. I would say that this molecule has 6 pi electrons, and they are all in the conjugated pi system. And they are all in the conjugated pi system. Let me change this real quick. Let's use green. Okay. A hallmark of the conjugated pi system is that you have 3 or more atoms in a row that are sp2. So another way to think about this is that you have 3 or more sp2 hybridized atoms in a row. And by the way, the hybridized atoms do not have to be neutral. Check this one out. If I have this molecule here, and I'll have this positive, we all know that the molecule looks like this: C, 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 and we have, how am I going to draw this? We have 2 H's here. We have 2 H's here in the carbocation, and we have 1 H right here. Okay, and more importantly, each of these atoms are sp2, 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 even the carbocation sp2. Does that satisfy our definition? Yeah, it is 3 or more sp2 hybridized atoms in a row. That constitutes a conjugated pi system, even though one of them is charged, and also you don't see any pi electrons here, right? Where are your pi electrons? And go ahead and jot this down. You have p orbitals, and I typically make them red, but you don't have to. And they're perpendicular to the sigma bonds. And they are aligned with each other. P, P, and P. And look where the electrons are. Doesn't 2 electrons make a pi bond? So here's 1, and here's 2. And so there's communication or overlap of these p orbitals, and those 2 pi electrons are in those orbitals. But remember, with the carbocation, you have an empty p orbital, but they are also aligned. So in what I would conclude here is that there are 2 pi electrons in the 3 atom pi system. So why is that important? the electrons are shared between 3 or more sp2 atoms, are shared, or let me put this, the pi electrons shared between, in this case, 3 atoms. And here's the deal. Last semester we had pink phrases, something to memorize to make sure you know a key concept or you don't get a concept backwards. For instance, like equilibrium favors the weaker acid. Here I'm going to say, I forgot what I was going to say. The pi electrons are more stable when, remember the word delocalized? Delocalized. That's the stabilizing effect. And so the conjugation is, we'll put it up here, is a stabilizing situation. Okay, so let's practice, and I'll get to the specifics of the aldol reaction and the enolate stuff that we've been working with. But let me give you a very simple problem. We have these 3 dienes. Okay, dienes are 2 double bonds. Oh boy, maybe just 2. Versus this. Guess what? This one's more stable. This is the more stable diene. And we could call it a conjugated diene. It is a... Are you starting to understand the terminology and how to use it? This is a conjugated diene, while this on the left is a non-conjugated or isolated diene. Okay, a few good examples. Now imagine if you had even longer conjugated systems. Imagine if we had more carbons that are sp2. Heck, we could even have an oxygen that's sp2. How would that work? Here, there. So this carbon and this oxygen are both sp2. And we saw that with the aldol. And for my class, I tell them if you can make it conjugated, okay? Don't stop at the beta hydroxy carbonyl. For instance, just a real simple one. Let's take this one here, and let's do a self-aldol. You could use NaOH or even NaOET. I like to match the solvent with the base, so the R group of the solvent's the same as the R group as the base. I tell my class you don't need heat to make a molecule conjugated, and that is, I think, in the minority. The textbook often says you got to add acid or heat to cause it to do conjugation, but I say the conjugated system is a more stable product. Eventually, it will get to that product, and so I will make this conjugated. 1, 2, 3, 4. Okay. At some point, you'll be that fast, or you're probably already that fast, some of you, to draw the conjugated aldol product. So this is the product of the aldol conjugation. Okay. Now, can you imagine if I had something like this? I don't know. Like that? Oh boy. Like that. No. Like this. Yeah, forget it. That was good enough. Like that. Well, if I do the same conditions, you'll realize that I cannot get conjugation. I think I cannot get conjugation. So here are my methyl and my ethyl out of the way. I like drawing the alpha and I like making the connection to the upper right. And so let me put a dot because I'm getting lost. Dot, 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 dot. And on that dot, okay, on that dot we have 3 more carbons, 1, 2, 3. And if I try to put wait a second, we're missing something. We're missing a methyl group right there. Double check, dot, carbon methyl, and then ethyl. Dot, carbon methyl, then ethyl. Okay. I cannot do this, guys. Yikes. We have a Texas carbon right there. A carbon with 5 bonds. So this is no good. X. And we have to stop. We have to stop at the aldol. And we cannot get conjugation in this case. We cannot get conjugation. You know why? Because we have no hydrogen at the alpha position when we get to the aldol product. So the thing is, you need at least 1 hydrogen to make the enolate, and then another hydrogen to remove in the dehydration. This one only has 1 hydrogen, so we're able to make the aldol, this one right here, but we're not able to do a proper conjugation. Now, would you be able to do a dehydration? Yes, but under basic conditions, you would not do a dehydration if it was not conjugated. Under acidic conditions, you remember acid catalyzed dehydration, and yeah, you could make the double bond right here, right to the right, and get rid of this OH. Okay, but that's not conjugated. So in these conditions, I would stop at where the smiley face is, and this is your final product, which is different than what we had up here, where the conjugated system is the final product. Again, take a look at your orbital cartoon. So let's draw the orbital cartoon for this, at least the pi system. Let's draw the pi system orbital cartoon. So I'm going to draw it slanted. Okay, so we have O, C, C, and I'll draw another C. Okay, do you see where I'm going with this? All right, maybe you don't see. 1, 2, 3, 4. 1, 2, 3. Oh, let's put a C here. Okay, that oxygen right here is sp2 hybridized, and so let me draw the p orbitals. Okay, let's see. We have 4 atoms, I think, in conjugation. That carbon next door, sp2 again. All I'm doing is looking at this here. sp2, 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 sp2. sp2, sp2. There is a pi bond between the O and the C. So let's put those 2 electrons there. There is a pi bond between these 2 carbons, the alpha and the dot. Should I do that? Should I put the dot and then should I put the alpha? I don't know if this is helpful. So we have a double bond. Okay, what do you notice about the p orbitals? They're all incommunicado with each other. And so this is a very stable system, and in my mind, you will make it even without heat or acid. So there's your delocalization of the pi electrons. We have here a 4 pi electron, 4 atom pi system. You want to draw the other electrons for oxygen. Remember, it is sp2 hybridized, right? sp2, sp2, sp2. So here are your 2 lone pairs. Do you see that? And here's your 1 electron. 6 valence electrons for oxygen. We can do the same thing with carbon. It has 4 valence electrons, but I don't want to clutter up the drawing, but you understand there's an orbital here, and this one here, the last one was probably could make a bond to this carbon here, the third sigma bond, etc., etc. One last thing, and then I will end the video. Oh boy, I thought I had more space. Multiple choice. Which one of these cannot make a conjugated system when you do an aldol? Which one cannot complete an aldol condensation? How about that? Multiple choice. This one, this one, or this one. I'll leave that for you and your classmates to discuss. Zoom out. Okay, that's a pretty good sheet on conjugation. There is more besides the aldol that forms conjugated systems. Most likely, my class and typically any other class following the textbook will do conjugated dienes, mainly molecules that look like that. And there are some very special reactions with those.